Welcome back to CS520. Today I'm going to talk about Intel 64 instruction encoding. This topic is a little bit complicated. I'm not going to give you a comprehensive review of it. We're going to cover the basics, and I'm going to rely heavily on an Intel manual that's divided into two volumes, two sections. Volume 2, which is divided into two sections, talking about the Intel 64 and IA32 architectures. The first volume, actually, chapter 2, talks about the overview of how instructions are encoded, and also includes a description of all the opcodes whose mnemonic starts with A through M. And then the second volume talks about all the opcodes whose mnemonics are N through Z. So let's jump though back into section 2 of the first volume and take a look at the instruction encoding. And the first thing you're going to notice is it's a variable length encoding. And it's got a lot of components. So again, this is a complex encoding for a complex machine. And again, I'm not going to go over every last detail. I'm going to try to focus on the main things and give you a basic understanding of how things work. The first thing to note is that the opcode is sort of here, and it could be either 1 byte, 2 byte, or 3 bytes. And in fact, we'll see the opcode sometimes leaks over into this next byte too. So again, a complicated situation. And in many cases, we have to start the instruction with a prefix. In particular, we're going to be looking at encoding operations on 64-bit operands, and that requires us to have a prefix that tells the machine to use a 64-bit operand. Because again, the machine is historic. It came up from a 16-bit word to a 32-bit long word, and now has been enhanced again for a 64-bit quad word, and the instruction set has had to be updated every time. So the way they made this last jump from long word to quad word is they had to add a instruction prefix that allows us to say we're operating on quad words. Okay, the next byte here is this mod RM byte. It allows us to describe the addressing modes used. So is the operand in a register? Is it in memory pointed to by a register? Is it in memory pointed to by a register and a displacement? Is the displacement 8 bits or 32 bits? So there's some choices to be made there. And also, this is where we designate what registers are being used. Sometimes this byte isn't enough, and there's actually another byte, the SIB byte, that is used. I'm actually going to skip over. That's one detail I'm not going to talk about in this lecture. Finally, the instructions might have displacements. So again, an addressing mode where you're addressing a location in memory pointed to by a register, but where the register address, the address in the register is adjusted by a displacement. So for instance, if you think back to addressing parameters or local variables where we're doing something off the frame pointer, the displacement, that's the distance, is the something, right? How far away from the frame pointer is the operand we're trying to get. The displacement actually would be stored in the instruction here, or sometimes we're doing an immediate operand. In other words, a constant value that's right in this instruction, it would be in here. And notice these can be variable length, 1, 2, or 4 bytes. And the mod RM byte, again, is 3 components. Choose the addressing mode with the first 2 bits, and you just specify the registers in 2 3-bit fields that fill up the rest of that byte. Again, fairly complicated. Let's dive into that mod RM byte right in here. Take a closer look at those 3 fields. Okay. So the top 2 bytes, as I said, specifies the addressing mode. I got 2 bits. Yeah, I said top 2 bytes. I meant top 2 bits. Specifies the addressing mode, and we have 4 possibilities with 2 bits. So 0, 0 means the operand is pointed to by a register. 0, 1, it means it's a register plus a displacement, where it's an 8-bit displacement. 1, 0 is a register and a displacement with a 32-bit displacement. And the last case, 1-1, is the operand is actually just a register. Okay. Middle 3 bits are going to specify a register. Sometimes the opcode leaks into these 3 bits, so it's actually used to extend the opcode and choose the particular operation that's being performed. The bottom 3 bits then specify the register memory operand. Many of the instructions, the Intel instructions, operate on a register plus a register or a memory operand. Okay. So again, these are 3-bit fields that usually specify a register. So let's see how the register codes work. Right, again, it's 8 bits. Sorry, there's 3 bits, which provides 8 possibilities. And we have 16 registers, as you remember. The 8 historic registers given on the left, and the 8 newly added registers for the 64-bit version of the architecture here on the right. So there has to be a bit somewhere else. It's actually in that first prefix byte. It's going to be a bit that selects whether we're talking about a traditional register or a new register. So there's a bit somewhere else that makes that distinction. And then there's these bit patterns that select which of the 8 different register pairs is going to be operated on by the particular operand specified by this mod RM byte. Okay, so it's just encodings for the registers. So again, that prefix byte is where we would choose between the old version of the registers, or the new registers that were introduced in the 64-bit architecture. So let's take a look at that prefix byte. It's called the REX prefix. I guess that's for register extension. Register extension byte, REX prefix always starts with 0100, so it's always going to have a hex 4 as that first nibble. And then the bottom 4 bits specify 4 different things. The rightmost one extends the mod RM register memory operand. So if this bit is set, then we're operating on one of the newly introduced registers for that particular operand. This second bit from the right is an extension of the SIB byte, which I'm not going to talk about. This third bit from the right is an extension of the mod RM register for the operand that's just a register. So again, if the bit is set here, it means we're using one of the newly introduced registers. If it's clear, we're using one of the traditional registers. Finally, the leftmost bit of this nibble is turned on to indicate that we are operating on 64-bit operands. Okay, I think those are the key building blocks that we need to understand the examples I want to show you. And here's the first example, which is just a function that operates on quad words and adds its 2 parameters together. And I'm showing you a display that's the output listing from a GNU assembler, which the GNU assembler we can run on our system by just saying LAS for the assembler. And to get this listing, I used the -AL flag, and then I gave the file that I wanted to assemble. Okay, and the listing's quite nice in that first of all, the leftmost thing is just a numbering of the source line numbers. The second column is the address in the object code. The third column is the object code itself. And the fourth column here is the original source code. And one thing to note is that these assembler directives here, .text, .align, .global, don't actually result in any executable code. There's nothing over here because they're just directives to the assembler. Likewise, this label doesn't end up in the object code either because it's just telling the assembler to use this name for the beginning address of this first instruction. Okay. Let's just review the code real quick. We can see it has the typical startup code that all good Intel functions do, right? They push the frame pointer and they establish a new frame pointer. And likewise, the shutdown code is just reestablish the frame pointer by popping it from the stack, okay, and then do a return to reestablish the instruction pointer. In between, we just have two instructions. Remember that parameters are passed. The first parameter is our RDI. The second parameter is an RSI. So I'm adding RSI to RDI here. So I'm just adding the two parameters together with the result going into RDI. And then I want to return that result, and we know the convention on this machine is to return values in RAX. So I have a move quad word instruction to move the result of the addition into RAX before I do the return sequence. So that's just a quick example, yet another example of an Intel 64 program. All right, so let's look at how it's encoded. Right off the bat, this push quad word instruction is a special case. It's actually, the way it works, it's a 1-byte instruction. So it's designated as 50. Again, I'm going to be writing these numbers in hex, 50 hex, because that's what this displays in. This encoded instructions are being shown in hex here, as is the address, I guess. It's 50, and then in the bottom 3 bits of that, we are putting the 3-bit register code. So I wanted to push RBP so RBP is right here, 101, right? 101. So that's 101. I'm adding that. That's hex 5. So the instruction itself, as you can see over there, is 55, right? 55. And again, another unusual case in that the opcode really only uses the first 5 bits, and then the register is crammed into the bottom 3 bits of that byte. Okay, again, a complicated encoding scheme on this machine. Okay. Let's look at the move Q instruction. Move Q instruction is going to use the rex prefix, the REX prefix. Prefix byte is 48. Again, that's the rex byte. We're interested in those bottom 4 bits because all rex bytes start with a 4. Bottom 4 bits is 1, 0, 0, 0, right? So all it's doing is it's telling us that we're operating on quad words. By the way, you may be wondering, why didn't we need a rex byte on here? And I think it's because the machine on the push instructions, it's looking, to another control register that indicates what's the standard size being pushed onto the runtime stack. So it's sort of looking somewhere else to see we're running in 64-bit mode, and therefore we're pushing quad words. That's why there's no REX byte on that first instruction. Right. So 48 is a rex byte just telling us that we're operating on 64-bit operands. 89 then indicates the opcode, that it's a move instruction, and in Intel assembler format, it's a register or memory of 64-bit operand and an R, a register of 64-bit register. Okay. So that's just choosing the opcode essentially, and then we have to specify which registers are being operated on and what addressing modes are being used, because this 89 opcode could have a memory operand in this instruction, or it could be a register. So it has to be designated here in the mod RM byte. So E5 is 1-1. That's indicating that that this operand will be a register actually. And then it's 1-0-0, which specifies RSP, and 1-0-1, which specifies BP. Again, we're using traditional registers that existed in the 32-bit version of the machine, because these 2 bits are not turned on. All right. So again, that's the encoding right there. All right, let's look at this move instruction. Again, we have the rex bit on the front, the rex byte on the front. The add is a 01. That's just the opcode for add. And then we've got F7 to specify what the operands actually are. So F7 again is a 1-1, indicating that the operand that possibly could be a memory operand is in fact just a register again. And I have 110 indicating it's RSI, and 111 indicating RDI. Again, the 8 over here, that bottom nibble of the rex prefix is, sorry, that should be an 8, 1000. So again, we're working on registers from the traditional register set, because these bits are clear. Okay, then we have again, that's 4801 F7. Okay, we have another instruction here, another move quad word instruction, again starting with the 48 prefix. The move, again, as we saw above, is 89. And we have F8 this time in the mod RM byte. F again is 1-1, indicating register. And I'll have 1-1-1 and then 0-0-0. 1-1-1 is RDI, and the 0-0-0 is RAX by our 3-bit encoding. Again, that's an 8, so we're using traditional registers. I meant to show you along the way, let me back up, how you'll see these things in the Intel manual. Let's go back and look at the push quad word. If we look the push quad word up in the manual, you're going to see something like this, right? A whole bunch of possibilities for push of different flavors. The one we're actually using here is this one, where we have 5-0 plus a register designation. It's doing the push, 64-bit push. Default operand side is 64-bit. You can see the same opcode is used whether we're pushing 16, 32, or 64, and it's distinguished by CPU knows the default operand size for the runtime stack. There's a bit somewhere set in a control word that controls that we're running in 64-bit mode for the runtime stack. Okay. Likewise, we can look up the move instructions. Right, we were doing a move quad word a couple times here. You look that up in the Intel manual. This is the one we're actually using. Again, you got to be careful because it's in the Intel format. I guess we can't tell the difference because we're moving between 2 registers in these 2 examples. But again, the Intel operands are listed RM64 first, followed by R64. The Linux assembler would actually reverse these operands. That's what's confusing. You got to be careful, when you're looking at documentation. Remember that this Intel documentation is using the Windows assembler, and that's different than the Linux assembler. Okay, but again, it's saying you need to have the rex prefix, and then the opcode is 89. And finally, we can look at the add as just one more example of looking into this manual, trying to make it so you're not too intimidated. You look into the manuals if you need to do that ever. Again, the add instruction that we're using is this one with an opcode of 01. It's saying we need to have the rex the REX prefix, and it's going to add a 64-bit register to either a 64-bit register or to a memory operand, a 64-bit memory operand. Okay, so it's a little bit about what the manuals look like. Let's go back and finish this off. We just have to do the final two instructions. That's part of the standard shutdown sequence. The pop is just like the push, is that we don't need the REX byte, and in fact it's just a 1-byte instruction where it's 58 plus the register specification, which in this case we want RBP, so that again is a 101. Whoops, 101. But in this case we're adding the 8 to the 5. That's a 13, which means that the opcode actually is 5D. Okay, again, the 101 is the specification for RBP, and that's added in as the bottom 3 bits of this value. So again, that's a special case where the opcode really is only taking up 5 bits, and that register is squeezed in as the bottom 3 bits. And finally, the last instruction is the easiest situation. There are no operands. The return instruction is just denoted by its opcode C3. Okay. So that's example. Let's do a couple more examples before we quit. I guess I need a fresh piece of paper here. So let's look at the move quad word of an immediate constant. So I have move quad word, and I'm using a Linux assembler now, $1 to register RCX. So we're looking at the encoding of an immediate constant. Well, it's a move quad word. So I'm going to need the REX. And I'm going to go with the REX with a 8 for the nibble, so because I'm just using conventional register here, RCX. The move instruction itself is C7. And I looked that up in the assembler manual. It's going to be move RM64 with an immediate 32 constant. Let's just check that out. Let's see. Yeah, it's on this sheet also that I have. Let's just take a look. So it's this one down here, right? REX byte C7. It's doing a move this immediate constant into either a memory location or a register. So again, the mod MR bit RM byte is going to have to explain what exactly is going on. Okay. And I'm going to want to use a C1 actually for that mod RM byte. C because in fact I'm moving the immediate constant into a register, so that's the left 2 bits, saying that the operand is a register, not a memory location. The middle 3 bits here are unused, essentially, because of because it's an immediate mode. The opcode tells me it's an immediate mode. So you could think about this as being unused, or you could think of this as concatenated. It's part of the opcode, if you wish. And in the bottom 3 bits specify this register, right? So 001 is RCX. And then the immediate constant, I've chosen to use a 32-bit constant. It will be in little Indian form, 01, 00, 00, 00. Okay, I could have chosen to represent this with a shorter instruction because the value is only 1. So I could have chosen to use an 8-bit Let's just go back and look what my choices were actually. Go back to the move. I could have used either 16-bit or 32-bit. And I have to read the fine print closer. Could I have done an 8-bit one here? These triple. This looks like I can't in 64-bit mode if I read the footnote here. But I could have certainly chosen either 16-bit or 32-bit. Sorry, 16-bit or 32-bit immediate constant here. For whatever reason, I chose a 32-bit one. So I'm going to have 4 bytes at the end of the instruction carrying the immediate constant. All right, let's do one more example and we'll quit. Okay, so let's look at an example with a displacement. How about move quad word R9 to a memory location given by 16 off of the RDI register. Okay. So I'm moving the contents of R9 to the memory location given by adding together RDI with displacement 16. So because we're doing a quad word operation, the instruction is going to start with a prefix. In this case, it's going to be 4C. Remember, the 4 indicates it's one of these register extension prefixes. The C is 1100 if we break those bits down. And again, the leftmost bit is because we're doing quad word operations. This bit position corresponds to the register operand and is set to 1 because register 9 is one of the new registers. The middle bit here is for the SIB, which we're not talking about and we don't need in this example. And the rightmost bit here is for the register memory operand, which denotes here. And because RDI is a traditional register, we don't set the bit here. Okay. The opcode we want is 89, which is a move instruction. It takes a register memory 64-bit operand and a register 64-bit operand, and it actually, if you look at the description, it moves from the register to the memory operand. Again, this could be either a register or memory. Okay, so up here, this is the R64, and this is the memory, the register or the memory 64. Okay, so that's the opcode. Then we're going to have a mod RM byte to describe the actual operands in more detail. And I want an 8F here. Remember, this is a 3-bit field, sorry, 3-bit fields. Left 2 bits indicate the actual memory addressing mode used to describe this memory location. And bit 10 is the code for a 32-bit displacement off a register. Again, I'm choosing, for whatever reason, to represent this displacement in 32 bits. I could have done it with a shorter, I could have done it in 8 bits, I believe. Okay. What about the other bit fields here? There's going to be, the middle bits are going to be 001 indicating R9 because those 3 bits go with the register operand. The register operand here, the register operand. Okay. And then the last 3 bits are 111 denoting RDI because those 3 bits describe the register or the memory operand. In other words, this operand. Okay, so that's where the 8F is. 1000, that's 8. 1111, F is F. Okay. Now I have to describe the 16-bit, I'm sorry, the displacement of 16. And I've decided to use a 32-bit displacement. Again, this is decimal 16. So the displacement I want to store in hex is 10000000. Okay, so in the end I have a 7-byte instruction, 4C, 89, 8F, and then the 32-bit displacement 10000000. All right, so that's enough of this. Let's stop here.